In this video, we're going to be going over the basics of hydrostatics. So, hydrostatics are going to be similar to problems that we've solved, except for now we've got to find the forces exerted on an object due to water and some water force. So, if, for example, we've got some gate sitting in the water here, and it's held up by some sort of pin system up here, and there's some stopper over here. And let's just say there's some water over here as well. So this water here is going to exert a resultant force on that gate there. And then, of course, that gate is going to have your typical reactions that we've seen before. And then you can analyze and design that gate from those forces and reactions that you calculate. But the main thing here is that this water is going to exert a force onto that gate, and we need to be able to calculate that force that's coming from the water that's acting on the gate. So the first thing that you'll want to do is find the pressure of water. At critical points on your object. So these critical points here that we're talking about, it's going to be that part on the object where the water first starts and at the very bottom. These are going to be your critical points, those critical locations where the pressure is going to start and where the pressure is going to end. And so you're going to calculate pressure by taking the specific weight of your water or whatever sort of liquid you have over here. It doesn't necessarily have to be water. And then multiply it by the depth from the top of the water down to that point of interest. So that there is going to be Z. And Z for the critical point at the top here is just going to be 0. So pressure up here is going to equal 0, which makes sense, right? If you're at the top of the water, there's no pressure, and then as you move down, your pressure is going to increase. So once you have your water pressure, this will give you units of force per area. So some area force. So if we draw a 3D version of this gate, so this gate here is this gate here. We're just looking at it in 3D now. So we've got water acting over here now. And so now we've got this area force, and we want to get it into just a line load. So a PLF, a pounds per linear foot, a force per some length, because then we can just treat it as a distributed load and we know how to analyze those. So we're going to call that our intensity function. Which is denoted by omega. And that's going to be equal to your pressure force times the width of your object. So in that case, the width of our gate is going to be that distance there. So if we're looking at this one up here, it's going to be that length into the page that that gate is going. So this is going to be your width. And that will give you your intensity function, which, like I said, is going to be a force per length, which is just a distributed load. So once we have our intensity function, then we have a force per linear foot, or a force per length. So force is going to increase as you go down. As you go deeper in water, it's going to increase linearly. So we're going to have something that looks like that, where this length here is our omega that we calculated right here. And now, if we just rotate that clockwise 90 degrees, we literally have this distribution here. Which is just a distributed load. So now, you're going to use the same things that we used, the same skill set, the same things that we learned from distributed loads to find your resultant force. So we know that a resultant force from some distributed load is just going to be the area of that shape. So for us, we have a triangle. So it's going to be the area of a triangle, which is 1/2 base times height. And so we know 1/2, and our base in this case is going to be our omega, and the height of our triangle is going to be the length of that gate or that wall or that dam or whatever object that you're looking at. So let's go ahead and look at an example of one of these. Let's just make it really simple and say we've got a 10-foot high gate of some kind, and there's water that goes all the way to the top. We always denote water with that little triangle thing, just so we know where the surface of the water is. That's just typical nomenclature. Let's also define that the width of that gate is 30 feet. All right, so the first thing we need to do is we need to find the pressure at the critical point. So in this case, we're going to want to look at the top of the gate and the bottom of the gate. But we know at the top that the pressure is going to equal 0 because your depth is 0 at that point. So we automatically know that from there on out, all the other equations up there are going to be 0. So that's all right. We can just not work that one out at all. But we do need to find the pressure down here. So P is going to be equal to gamma Z, which is going to be 62.4 pounds per foot cubed, times Z, which again is from the top of the water down to your point in question. So that's just 10 feet. So that's going to be 624 pounds per square foot. Then once you have your pressure, you can find your omega at that point, which is going to be pressure times width. So 624 PSF equals 624 PSF times the width, which was 30 feet, and that equals 18,720 PLF. And so if we redraw our gate, We know that pressure intensity is 0 up at the top, and then we know down at the bottom it's going to be 18,720 PLF. And then you just connect those with a straight line. And you've got that loading action there. Again, if you just rotate that 90 degrees clockwise, you're going to end up with this loading here, which we've seen a million times and you know how to do. We can get a resultant force of 1/2 base, 18,720 PLF, times height, which is the length of that gate, which was 10 feet. And you will get that the resultant force is 93,600 pounds, which is also 93.6 kips. And then again, the location of that resultant force is going to be the same as when we looked at other distributed loads. It's just going to act to the centroid of that triangle. So we're going to have our resultant force here. And that there is going to be 1/3 of that total length, which was 10 feet. So that there is going to be equal to 3.33 feet. And it's really as simple as that. Find your pressure, find your intensity, find your resultant force. Once you get your intensity, it is just like the distributed loads that we did beforehand. It's nothing different. So don't let it freak you out. If you have any specific questions on homework problems, head over to our homework help page. We will get you help there. Or if you're just having trouble grasping this concept in general, feel free to visit our tutoring page, and we'll be able to sit down with you and explain things there.